Good afternoon. I would like to welcome all of you inside and online participants on our next quantum computing seminar. This time, the speaker is Dr. Bhattacharya, who is now a researcher at the Technical University of Ostrava, and he will give a talk about quantum gate neural networks. So, please, audience is yours.
Thank you very much for inviting me. I hope I'm audible to all of you. So this particular topic, in fact, I am just going to introduce to you what is quantum gate neural networks. So you know that quantum computing is now a booming topic, and people are looking like to it like anything. So the objective is to combine the principles of quantum mechanics or quantum computing with computational intelligence to get some quantum machine intelligence tools. So quite obviously, the first and foremost task will be to design quantum neural networks. So how to design quantum neural networks using quantum gates on a superconducting device. That is the primary concern of this particular topic. But then before that, we'll be having a walkthrough from the quantum inspired to quantum domain, because we are transiting from the classical domain to the quantum domain. So obviously there must be some transition period between them. So in fact, our group started working on this particular field way back in 2006-7, when there was no IBM quantum as such over there. So we started with this quantum inspired domain, and then now gradually we are just transitioning into the quantum domain, pure quantum domain, where you can have quantum neural networks. So as we move on, the agenda for this particular topic will be just touching upon the classical neural networks, and then quantum inspired neural networks, taking the philosophy of quantum, how to design quantum inspired neural networks. Then coming the remaining topics will be pertaining to the quantum gate neural networks, like TensorFlow Quantum Circuit, Parameterised Quantum Circuits, using variational quantum circuits, and then how to train the quantum neural networks. If at all, you can design them on a quantum gate machine. And higher level PQCs, higher level parameterized quantum circuits, how to go for the abstraction of that particular parameterized quantum circuits. And obviously coming to the optimization of parameters, because you know these are all variational circuits. So you have to have some parameters over there. So you have to optimize the parameters. So the right choice of parameters will give you the correct result. And some examples as to how you can design a quantum variational autoencoder, and some advantages finally. So you see, this is quite relevant to all of you. You know what you do very well. Just to brush up the knowledge over there. So you see, this is the left-hand figure. No, this is not working. Anyway, just hold on. The left-hand figure is the, you see, the left-hand figure is the topology of a neural network, classical neural network, but your input values x1 to xn in vector form, and your weight matrices, which are the connection weights, and then you get some summation over here as a logistic function over there, and then you get the output. Pretty simple. And once you get the output, obviously due to the random nature of the weights, you will get a random output. So what is the objective? Your objective is to reduce this. That is, this is a supervised architecture where you have the knowledge of the output in advance. That means there is a relationship between the output and the input. You know it very well in advance. So since you know that, so once you get some random outputs over here, what you do, you compare with the actual or expected outputs, and then you get some errors. So use the errors to adjust the weights accordingly. We are using backpropagation algorithm, which is a very time-consuming process anyway. And then once you adjust the weights, you start all over again. You provide the x1 to xn inputs again, just to train the neural network with all sets of combination of inputs. And if this goes on, this process goes on until the weights are stabilized, and you get some errors which are below some tolerable limits. But you cannot make them zero. Why you cannot make them zero? Because of the fact that the logistic function or the activation function generally has this particular cost. Maybe either logistic function like the symbolic activation function. So here it is symbolic activation function. You see, it is asymptotic in nature. It never touches 1, never touches 0. That is why you always get some errors. Maybe small. The objective is to make it as low as possible. Or you can use either tan hyperbolic or softmax. Now, RLU is quite used nowadays after the advent of deep neural networks, or some plus or other models also there. So this is a picture of a fully connected neural network, but the inputs and different number of hidden layers will be there, and then the output layer. So it depends on the complexity of the problem. Now, these are the quite characteristic equations where you have these outputs coming there, and then you adjust the weights by using the derivative of the outputs with respect to the weights. Why? Because weights is the main culprits. Because weights being the random, they are producing random outputs. Because the inputs are fixed. So since the weights are random, you are getting random outputs. We have to adjust the weights, adjust the errors by taking the derivative of the output and the cost function with respect to the weights. So you adjust the weights accordingly, also you adjust the bias, because there is another separate input bias over here, which actually controls the operation of the neural network. Anyway, so this is quite very simple, you see. It can be implemented easily on a classical machine, but you see this process from here to here and then coming backward, backpropagation, and then again moving on. So this is something iterative in nature. But in quantum gate neural networks in pure quantum domain, very difficult to achieve iteration, because you cannot do iteration in a quantum machine. It is a one-shot process. So that's why we started all over again with something. Just hold on. I know this is actually, I've just put it over here, is some taxonomy of all possible neural network architectures, starting from the basic perceptron to feed forward, and then coming on to the deep neural network versions, deep convolutional neural networks, generative adversarial networks, all different types of topologies, just for the sake of completeness. So what we thought, why not come up with something which is quantum inspired? The problem is that what the advantages you are going to get from this. First of all, you have to take into account the advantages which the quantum computing domain is going to offer you. Why don't you take the advantages over there? So you see, quantum computing, what are the advantages it offers? Massively increased computational efficiency. Quite obvious, because you work with super. Yes, please. So you see, so massively increased computational efficiency for quantum computing is offering. Why? You know it very well, because it works on the principle of superposition. So once you superpose two solutions, superposition means you have a galaxy of solutions all at once. So the point is to pick out the best solution out of that. So devise some algorithms to pick out the best solution. Because quantum computing is giving you all possible solutions at once, simultaneously. So that is one important advantage you are going to get if you just try to conjoin quantum computing with neural networks. And then potential for bridging brain and mind, but obviously increasing relevance, because we are going into nanotechnology. And you are using the principles of wave function, superposition, entanglement, unitary transformation. These are quite well known to all of you, because these things are quite common for any quantum computing platform. And you want to inherit the advantages given by these particular features to your own classical neural network to make them more viable and more efficient as such. Now, before moving on, there are some problems, quite obviously. If you want to have a quantum inspired subcomputing, there are some problems. First of all, quantum computation is linear theory, nothing non-linear over there. But ANN is non-linear. So you have to conjoin one linear approach with a non-linear approach. Why ANN is non-linear? You know, it is already given some picture over there. It comprises of processing elements, neurons, and then some transformation is being done by the elements of the neurons, and then the interconnection structure, weights, network dynamics, which actually governs the learning of the training of the neural network, and it is massively parallel. Now the problem is to merge these two together, how to process it. So only thing way out is to take advantage of the quantum computing in terms of the encoding. If you can encode the inputs using qubits, something like time superposition, then what you can do, you can use a nonlinear architecture of neural network to take advantage of the multiple inputs you are getting at the same time. Only this way you can do, apart from going into the details inside the characteristic functions of the neural network, only for the input part only. If you just try to use the advantage of quantum computing, you can encode the inputs in the qubits, first of all. And then let us go inside. If you go for the characteristic function, if you can think of something which is quantum in nature, maybe. Another thing is the interconnection between the neural networks. So if you think of something, some gates as such, for example, say, which can transform the same function as the weight function is doing on the inputs. What is the weight function? Or actually, what is the neural network? It is actually a multiplication of a vector input and a matrix weight. Nothing like that. Vector matrix multiplier. So some sort of multiplication which can transform the inputs by putting some gates in place of the weights. So how you can do that? Let us see. So there are several works over there. For the primary work we do to Kanamov, who came up with this quantum neural network architecture. And then you see, we visualized this one way back in 2006-7, I told you. In 2006-7 only. So we thought of devising a quantum neuron model, first of all. How to have a quantum neuron. So here are the inputs. I told you inputs are encoded into qubits. Anyway, you see, I hope it is now visible to all of you. Now it is a basic quantum neuron model. How we can envisage that? You can have the input like this, similar to the classical neural network architecture, which you show the picture in the first slide or the first slide. So the inputs are in the qubits form. KTX1, KTX2, KTXN. You have to encode the inputs. And then these are the weights. You see where's the rotation gates. Rotation gates only for manipulating how to rotate it. Just multiply the inputs with the rotation gates or apply the rotation gates on the inputs to get a new input rather. Because when one apply a rotation on a qubit, you will get a newly oriented qubit. That means that the manipulation of the qubit. Okay, fine. And this is actually the bias input, and you have the bias rotation gate for the bias. Okay, that's what we discussed earlier. And then here inside this neural network, you have two components quite obviously. One is the summation part, another is the logistic part.
Sorry, can you explain the mathematics of this?
I'm coming to that after all.
Okay, so you're going to say because that's
giving the picture only first.
Now that it doesn't make sense.
But I have not taken too much mathematics to make it more because I feel sometimes bored because I'm very weak in mathematics anyway. I will just try to just explain to you as much as I can. Okay. Just you can have the picture only. So you see, for example, very simple. You see there is a rotation gate like this. You are applying rotation gates on the qubits. So quite obviously rotation gates are applied on the qubits. Quite simple. So you have this and you take the summation. Now you see this is very important. You do not expect this to happen in a pure quantum computer. This is quantum inspired. I'm telling you. Just the transition between the classical and the quantum version. So you have this summation part coming out, which is the net activation of the neural network. And then you apply G delta. G delta is actually the sigmoidal activation function or characteristic activation function applied on this U. On what? On the argument part of U. Because you know, you will come up with two parts. One is the real part and the imaginary part. Because qubits are complex in nature. So what you do, you either take the real part or the imaginary part by taking the argument of U. And you apply the characteristic activation function on any part of them. Either you go for the real part or the complex part or the imaginary part, depends on your choice. Anyway, and then what you do after the application of this logistic function, you get some output y, which can be expressed as a function f of y. So the final output is given by s is equal to f of y, which is also in the form of quantum or qubits. That is, you are in a quantum domain. Now, what you do over here, you go for a measurement operation. Finally, you get the classical output because you started with the classical inputs, encoded them to qubits. Took out the operation inside the quantum inspired neural network in the form of qubits, trying to be in the quantum domain or being motivated by the quantum principles of quantum mechanics, and then finally you come up with some qubit outputs over here, go for a measurement and get to the classical output. But the problem still remains. Once you get the classical output, what about? It is not the correct output because it is going to be random output. Because you started with theta 1, theta 2, to theta and lambda, all these are random in nature. There is no perfect choice of parameters. So what you have to do again, you have to use the backpropagation. Now in this case, obviously, backpropagation will be different. It is referred to as quantum backpropagation. So quantum backpropagation means you are applying the backpropagation algorithm on the qubit outputs and then trying to adjust this theta, lambda, and delta, three parameters simultaneously. Why? Theta for the rotation gates, lambda for the bias, because these are all undecided because you have chosen it randomly. And this delta parameter for the also known as the reversal parameter for the characteristic activation function. So you have to adjust all of them accordingly and tune them so that the error comes down to an appreciably lower level. So this is quite a picture, or as I just think of a picture of a quantum neuron, basic building block of a quantum backpropagation neural network. Now, let us see how we can use it. So, as Professor was telling, we have some mathematics over here. So, take xi the input qubits. You can have any sort of coding, amplitude encoding, any sort of coding you can have. R theta as the rotation gets, lambda as the input bias. We will define a function in this form, fx is equal to f of x is equal to d to ix in this form. So what you have this u, that is the summation part, which comes out to n number of neurons, n number of inputs, sorry, and then you have this rotation applied on the qubits, xi. Minus f lambda, quite simple. F lambda stands for the bias, minus f lambda. So, sorry. Then what you do, you apply this sigmoidal activation function g delta on this u, on the argument of u. But g delta is given by this sigmoidal activation function. Now you see, interesting thing is that the sigmoidal function is characterized by this delta function, that is a reversal parameter. So this delta value choice is also very important. And then finally you get the s is equal to f of y is equal to, it is expressed in this form, e by iy. Because there are two parts, one is the real part and the imaginary part. And then you finally, if you go for a measurement, you get the final classical outcome.
Can we stop and look at the domains of these functions and images? And what are the inputs and outputs in the sense of types? Because what do you mean by ket of xi here exactly?
Ket of xi are the encoded inputs.
Mathematically, what this object is in your case here.
In your case, for example, I told you earlier that this is actually transition period. So, given some real inputs, because classical neural networks accept only real inputs, isn't it? So, you have some sort of encoding over there, maybe pi by 2 encoding, something.
Yeah,
like
okay,
that.
that's fine.
You have some vector. Xi, ket xi are the vectors. Okay.
Okay,
two
so
directions. Okay.
ket xi is a vector. In what space? What is the space it lives in?
In the Hermitian space, it's a vector like that. You have the vector where you have these two components. Just one is for the ket 0 and one is the ket 1.
Okay.
Now the choice is upon you how to manipulate that. Okay.
That's fine. So any state of the vector.
Pardon?
It could be any state.
Any state, because starting with, you see, I told you earlier, because these are actually the inputs are quite fixed. Okay. So it can be any state because due to the encoding process, it can be any state.
Should be initiated first.
I am not telling you. I am just listen to me. This is not pure quantum literature. Because when you think of some by using Hadamard all these things to get an equal superposition, all these things, I am not going to that. I am going for the transition part where you can have both the classical and the quantum together. Okay, please.
That's fine, but I want to understand the equations. What is the exact meaning of equations in the sense, what is u? U should be a vector.
Which one? U is a vector.
Okay.
U is a vector. I have got details over there. All these are vectors in that. I told you we are ultimately manipulating vectors with matrices.
Okay. F of lambda, therefore, is a vector value function.
Vector.
Okay.
Because you have a vector with a rotation matrix, multiply together, you get a vector, and the output is also a vector.
Yeah, okay. Alt of u then is not well defined because u is a vector.
U is a vector, but then you have both these two components. It's imaginary in nature, complex in nature. Okay.
Yeah, okay, but so alt of u then is applied to the elements of the vector.
Right. Right. Then you get a final output vector like that. Yes.
Okay.
And now it depends. You see, now you have to go for measurement quite obviously. Now, in the strict sense of term, you have to get in the qubit domain. You have to come out to the classical domain to get the exact nature of the output, whether it is corresponding to the expected output or not. Now, quite obviously, due to the random nature of the weights, theta 1, theta 2, all these things chosen randomly, you will come up with some random S vector. All the individual components are random in nature.
And this F here, it is a mapping from Rn into Rn, or just the function of one real variable.
Pardon? This one.
This F, yeah.
This one is just mapping Rn to Rn. No other.
It's defined like e to the power of
I. E to the power iy, to the form of e to the power iy, because we are taking into cognizance the imaginary part as well. The representation is like that, because any particular output, because the output will be of this particular form, you can express this in terms of f of y.
No, but so you mix the notation for vectors and functions defined on the elements of the vectors.
Pardon? Just
functions defined
yes.
of the elements of e to the power I y. It means that you take elements of the vector y,
yes,
and you produce. You apply. Okay, but that is unclear.
Let us move forward. Let us move forward.
Yeah. Okay.
Better off. Just for the time being, if you have this qubit neuron model as we have just proposed or as a design as such, you can just mark or to put them together like this in this fashion to have a multi-layer structure like this. Okay. But if the inputs over here, the hidden layer over here, and the output over here. Okay. And all are being guided by these weight matrices or rotation matrices, whatever. The inputs are out theta alpha 1, theta alpha 2 as usual to the single qubit neuron. And then finally, what draws out, you get two outputs depending on the number of classes you are dealing with. Maybe 1 or 2 or 3, depending on the classes you are doing. Very simple architecture of a 3-layer that quantum backpropagation you will get. So having the inputs over here, the outputs over here, and the hidden layer and output. So you can also go for increasing the hidden layers, number of hidden layers, depending on your choice. Okay. Now, if you come to the now just see the analogy between the classical neural network. One is one input layer of quantum neurons. So where the quantum neurons are superposition of qubits, which I already told you earlier, vector form, which access inputs in the form of qubits. Hidden layers several may be there. One output layer of quantum neurons, and connection weights are represented by single qubit rotation weights. So you are taking the flavor of quantum computing inside the classical domain to some extent, just to bridge the gap between classical paradigm and the pure quantum paradigm. Now the problem still remains because you cannot have an iterative procedure like that, which you encounter in classical neural networks. So you have iterative procedure where you can just have the backpropagation algorithm in the backward direction, adjust the weights, and then again you start all over again. But here there is no, because after measurement you come back to the classical domain. So what the way out? And just if you just want to be just to see it, coming to the basic implementation, inputs are real values, xi. We are scaled in that 0-1 range, quite obvious, and then it can be transferred to qubit. For example, one particular encoding procedure can be like this. Take xi, function of pi by 2 xi. Actually, that will be equal sign over here. Sorry, I missed it. It will be pi by 2 xi. One sort of encoding have used over here to just have a vector out of a scalar. Okay. To represent that in the form of 2 alpha and k, alpha k0 and beta k1. Now, quite obviously, I told you earlier that we are interested in either of the imaginary part or the real part. Then, if you take it the imaginary part, you take the because the entire mathematics has not been produced over here. Just giving the salient results over here. And now we just think of this something which is quantum backpropagation because we are dealing with some quantum is the domain, but the classical backpropagation will not do because ultimately you are dealing with the qubits in general. So quite obviously we have just taken only the real or imaginary part depending on your choice. Now what we need to do, as I told you earlier, because we started with random weights characterized by θ1 to θn. So we have to have this first parameter theta, we have to adjust accordingly because that is one of the culprits which is creating the fuss. The threshold lambda for the bias and the reversal parameter delta for the characteristic activation factor. So see, these 3 parameters are quite important if you want to adjust together. Now the interesting thing is that if you think of a variational quantum computer or variational quantum gate computers, you have these parameters over here, you can adjust accordingly so that you can have the best possible output as such. So it follows the principle of this quantum. Now the network error quite interesting, you know it very well. These are quite obvious. You have this error for different number of patterns. TNP is the output, expected output, and you get actual output you get, output NP. You take the mean square, you get the root mean square, you get the half of the square to get the corresponding output. And then finally, you come up with this adjustment, which is actually essential for any backpropagation algorithm. Adjustment of the error E coming up with respect to delta theta, or theta. Theta is one is the phase parameter of the weight connection. So you have this particular rule. I told you I didn't take the entire mathematics over here for what due to obvious reason. So the weight update equation will take this form. Mu theta will be the whole theta minus the zeta is the learning parameter, learning coefficient with this adapter. Similarly, you can here, this is quite obvious. This is the JK. JK means it is the hidden layer to the output layer. And now this is IJ is the input layer to the hidden layer. Input layer signified by I, hidden layer signified by J, and the output layer signified by K. So you have the two different approaches for adjusting the theta parameter is the weight parameter. Weight parameter means the angle of the weights or the rotation. Sorry. Similarly, if you just think of the again the forms are not coming anyway. Again, if you just go for the other adjustments in terms of this lambda and the delta, you can also obviously have the similar expressions for lambda and the delta accordingly in the both the hidden to output and the input to hidden layers. So now we apply this. I told you earlier that we have applied this to see how it actually excel the classical neural networks. We have compared it with classical counterpart, the classical MLP, because it is simply a reincarnation of MLP in the quantum inspired domain. So we just came up with this particular architecture, 4981, 49 input nodes, 8 output hidden layer and 1 output. Output 1 means it is going to just come out with two classes, noisy and non-noisy, two classes. So what is the objective? You have to apply this neural network to some noisy images, to to denoise the images, some blurred images to deblur the images. So this was the actual objective where we applied both this QBPNN and the classical MLP together and to see their performance together. So what we did actually, we used these two. Lena image, because at that time Lena was quite, it was free to use. Nowadays you cannot use Lena image as such. It has been forbidden. And the QLIP images, so you just see the different number of training patterns, 262, 144, something like this. So we just tried to assess the performance of the neural network based on image sampling and noise filtering. Two types of noises we have used, Gaussian noise and uniform noise, and see how it actually happened. Now this is one of the sample set of the training images. So you see, this is the original image, this is the blurred image, marred with Gaussian noise, marred with uniform noise at different degrees. Okay, some snapshot of the Lena image. Similarly, you also have the QLIP images also affected. Now, these are the training images which are used for both the neural network. One is the quantum-inspired backpropagation neural network and the classical neural network to see the performance. So, this you see the outputs. The outputs are quite subjective to human beings. We also have some objective assessment. So, these are the outputs. In the left-hand side, you have this quantum outputs. On the right-hand side, you have the classical outputs. So, quite difficult to adjust the performance of the quantum neural network. It will be quite clear if you go for the objective assessment. Now you see quite obviously that the blur has been just more or less removed. The noises have been tried to remove. But it depends on the subjective assessment. Now, to one of you, it may happen that these classical values or classical images are better than the quantum images. That depends. So you have to go for the objective assessment as well. Now, these are the examples of QLIP images. Now you see the network convergence. The convergence condition was decided based on the mean square error and the convergence ratio. What we did, actually we just set a target that the MSC of the output has to be less than 0.0015 in 5,000 epochs. We run both the neural networks of 5,000 epochs together and see which is achieving this MSC less than 0.0015 in the lesser time possible. What is the convergence you see? Now you see, if you look at the curve, this is this curve for the QBPNN, the quantum inspired curve, which is actually converging to this particular value profile at 742 epochs, compared to 3048 epochs for the classical neural network.
Can you restate what is actually the goal of the training? What is the input? What is the validation? I mean, what is the training set, validation set?
Training set I already told you. These are
the images, but what are the exactly
the pixel values, intensity values?
So you
encoded them.
Every single pixel.
Exactly. Every single pixel you have encoded them into qubits.
Okay. So you take pixels, and then those pixels are classified as noisy.
Either noise or non-noisy. And depends on different facets. You see, now you look at a pixel. If you look at a pixel, the neighborhood also matters.
Okay, but so you take also 49 by 49.
I told you that.
7 by 7.
Yes, exactly.
Okay.
If you just take a pixel, for the neighborhood also matters. Because a noisy pixel in all non-noisy neighborhood will ultimately be classified as non-noisy. That depends on the neighborhood actually. So depends on your approach.
Yeah, okay.
I told you 7x7 window was taken for the entire image, and then we just trained the images, and finally we just applied the two neural networks to testing. Finally, we arrived at this particular interesting.
Okay.
outcome.
Are those curves for training data or test data?
These are training curves. These are training curves, how they converge during training, because convergence is quite obvious because you have to ultimately reduce the errors to make them converge. That means the converge means what I told you earlier, you cannot have a zero error at any point of time because the function used is asymptotic in nature. It never touches 1, never touches 0. So quite obviously, there will also always be residual error at the top and the bottom. So the objective is to have a threshold limit. For example, in this case, we are doing this threshold limit just to see how the MSE is reaching 0.0015. It can be changed. That for the sake of observation, we run the algorithms or run both the networks for 5,000 iterations and see whichever is giving you the best outcome or that reaches the MSE in the shortest time possible. But in the case of the QBPNN, what we propose or tried to design is about 742, around 4 times lesser than the classical neural networks. Okay. Now, if you just look around to the objective quality of the images. Now, as I told you, from the images itself, it is quite difficult to appreciate which one is giving you a better outcome. Now, if you just look for the SNR values, see SNR values QBPN are higher compared to the classical one. Not only you are getting the convergence at a lower number of epochs, you are also getting good outcome. This actually helps in some practice. But the problem is that you see, these networks are actually implemented on classical machine. As I told you, we started this work, this work was published in 2006-7, when there was no IBM QCs or something like that, nothing was there. So these were ambitious to run on the classical machine but using quantum computing principles. Okay, this is a difference. Now, having this idea, what we have discussed till now, we have just discussed a generalized QBPNN model for expression of images from blurred and noisy perspective. And we have shown that the efficacy of the classical counterpart in terms of convergence and the convergence speed. Now, this is all about the transition period. Now, let us move on to the pure quantum domain, what we are actually now thinking of. This is the TensorFlow quantum. We are now talking about on this particular, we are talking very much on this because this is the actual backbone for helping you to develop hybrid quantum classical algorithms. Now the question still remains, why it is quantum classical? Because you cannot have, at this point of time, you cannot have a pure quantum, all quantum machine, all quantum algorithms, not possible. You have to take the help of the classical paradigm as well. So TensorFlow Quantum is a platform, Python framework, for helping you out this. It has all the inbuilt qubit registers, these algorithms, these Gaussian gates are also there. Or you can either simulate on a NISQ device, that is on a real quantum hardware, or you can just also implement on a simulator as such. So it is actually helps you. So how does it look like if you just look at the broader perspective? Now this orange figures actually for the classical values, and these blue ones are the quantum. So it has the provision for handling both the classical and quantum together. You start with the classical data, you can handle classical data and quantum data as well. Circuits and operators. Then you take the chaos model. These all the oranges are using the classical value of classical data, operating on the classical data, TM box, execution engine. And here you have these layers, TM quantum layers, and the differentiators for the quantum gradient descent. Okay. And then you have different operators. Finally, you have the SARQ also as well. Also, it is an open source framework from Google, which actually gives an abstraction of the quantum concepts to you. Finally, you can run on any particular platform you choose like. So it is actually a hybrid quantum classical platform. Okay, either you can run on a QPU or a CPU or a GPU or a TPU. Depends on your choice. Now, the understand is that classical and quantum go hand in hand. Okay. You cannot dispense with the classical values, no way out. So SARQ already have discussed you. It actually gives you the basic structures of qubits, gates, circuits, and measurement operators. So you can use that to your advantage to design algorithms and then run the algorithm. So the links already given. So this is actually circuit is a black Python like I told you. You can just go to the link and have the details. It is one simple circuit code example, very simple. Import the circuit. You see you are creating a grid qubit 0, 0. Then you're creating a circuit like this using this circuit command. Circuit and applying this poly X gate on the qubit to the power 0.5. Just taking the square root of the NOT gate. Okay. And then you measure it by using the measurement operator. And then what you do, you run it for 20 shots, for example. 20 shots, and then you get the results. Okay, so what you are getting over here, very simple code to just find out the the effect of applying the square root of a NOT gate on a qubit. So you have all the facilities available over here. You have all the gates over here, the qubits over here, the measurement operator over here. You can run at your own choice. But the algorithm is to be defined by you, so to take advantage of the quantum domain. Now, given this, let us come to or dwell into this actual scenario where you can have a quantum gate neural network. Now, as we have discussed, neural networks, there is a forward path to get the output, randomized output. Then there is a backward path to adjust the weight. Then again a forward path, but here you have something different because I told you, iteration is not a process in a quantum machine. You have to have something one-shot process. So what you can do, you can think of like this. You see, as I told you earlier, because there are 3 parameters. If you just look at or look back into the quantum space domain, you have the theta, lambda, and the delta, 3 parameters. Here also, you have this picture. If you just look at it, this is the quantum data preparation, where you have the fixed gates. You had a gates or C0 gates for getting the superposition or getting the quantum data. Maybe the different speeds, the electrons, and so. So these are fixed gates, quantum data preparation. And then you have the quantum circuit line, where you have to adjust the parameters accordingly. So these are actually VQCs, variational quantum circuits. Or parameterized quantum circuit, well, this circuit actually uses some parameters, which you can change or optimize depending on your choice, so that you can get the best possible performance. Regarding the training is as far as the training is concerned, that is training the quantum neural network to attain its goal. And then finally you have the output over the output here over there, after which you can determine something. So if you are interested enough, you can look at this paper from 2020 by Nature Publication. So this is the basic principle of a parameterized quantum circuit. So if you just look into the mathematical or the functional parts of this neural network, functional part, you see, I have told you earlier, the oranges are actually quantum, and the blue are the classical, hand in hand. You see the inputs may be classical, 1 0 1 0 or something like that. You have this Hadamard gate, a single gate following bell set. So this is the fixed gate operation. You are encoding the inputs in the quantum domain, and these are the actual for the parameterized quantum circuit. Where you have these theta values. Just recollect the theta in the case of quantum is where then the expectation of the value, that is after the averaging value and the absolute value. So here you have the inputs like this theta and all is back here. So these are actually, you are actually playing with the classical values, trying to adjust the classical values, so you get the quantum values, the appropriate quantum values to start to run the algorithm. And so this is this part. Actually, the second part is in case of implementation of the VQC, that is the parameterized quantum circuit, and this is the fixed gates for the encoding or encoding. So if you just think of in terms of implementation, first of all you have to do all these processes one by one. First is quantum computation instances, quantum models, sampling expectation, because at the output level you have to take several runs to get the sampling value. And differentiation also required for the adjustment of weights and the gate fusion. So the different gates using the QCNN operator to fuse the gates together to get the final output. Now, if you just see at the quantum neural network training model, how you are actually training. I just lost a glass of water. So you see that the picture is quite clear now. You cannot have a all quantum algorithm in place. So you see, these gates V1, V2, V3 for preparing of the quantum data set, encoding input data. This is the training part. This is actually training. Actually, the adjustments of the parameters are taking. This is actually VQCs, represented in a form of parameterized unitary matrices, U1, U5 to U5. These are also unitary matrices but fixed, not parameterized. And this is the evaluate quantum model. Then you sample, that means that take the measurement for different number of terms, and then you feed the output to a classical neural network. Why the classical neural? Because these parameters need to be adjusted accordingly. Because there is no right choice of parameters. If you could have right choice of parameters at the beginning, only one shot run will be sufficient. One plus run would not be sufficient. No. But you started all with the random value, so you have to adjust this parameter. So how to adjust the parameter? If you use neural network, you evaluate a cost function depending on the theta value. So this theta value is the parameter for the classical neural network. So you adjust the theta accordingly, so you get the adjusted value for the theta and the phi. So you feedback that the theta phi 1, phi 2, phi 3 updated one, updated by this classical neural network, and theta value updated one for this classical neural network. So you have a quantum classical together. Because you have to run it several times, because after measurement, all you want to get, you want to get classical value. So you cannot fit that inside the quantum domain as such. So what you have to do, you have to adjust the parameters accordingly, run it again. But now the inputs are being fixed. As is usual with the quantum neural network, inputs are fixed. You run the algorithm again, that adjusted parameters on the inputs. And then so you see the phi n actually are the quantum model parameters and theta represents the classical model parameters. So you have to have a classical neural network in place to adjust the parameters for the quantum neural model. You cannot have all quantum neural model or neural network in practice, given the state of art as of now. So what are the different steps of quantum neural network training? Prepare the quantum dataset using fixed gates. Evaluate quantum model using the parameterized gates, sample or average measurement. Evaluate the classical model using the outputs of the quantum model into the classical neural network. Evaluate the classical model. Evaluate the cost function to adjust the parameter theta and phi, and evaluate gradients and update the parameters accordingly. So TFO actually gives all the avenues for these particular operations one by one. So now if you just blow it up, together, it's very interesting, higher level. If you go to the abstraction level downwards, so you have to see, now the fixed gates are quite easy. Fixed gates will not change. Fixed gates have no parameters, they are only for encoding data set. Fine. When this come down to the parameterized quantum circuit, that's the U theta. So U theta actually means, if you just look at this, going from A, B, C, D, rather than going from this direction. You cannot understand. So U theta is ultimately final U theta matrix for the parameterized quantum circuit, or PQC. U unitary matrix with the parameter theta or phi, whatever it is. So actually this U theta can be represented as a collection of separate real theta. Real theta in cascaded fashion or in different fashion altogether. Each and every real theta can be represented like this particular as a collection of WJL theta just coming downwards in the abstraction. So different gates run together like this. And each W gate can be represented as in terms of a phase factor or a generator function, if I theta the Gj. Like this, atom 1 followed by phase function and followed by atom 1 function also. So ultimately it is boiling down to the lowest level of abstraction, that is the generator function Gj. Very interesting. Now, Gj can be represented in a fashion similar to the classical neural network weight into vector form. How? Now, if you are interested enough, you can just look into this particular paper. So, as I already told you, U theta can be represented by VL UL theta, where UL theta is parametric and VL theta is a non-parametric part. And then if you can just go downwards. So UL theta can be represented as a collection of several ULJ and theta LJ for J particular component. So finally, you can just boil it down to UL theta LJ in terms of a generator function e to the power I minus I theta L J and GLJ, which can be represented in terms of polymatrices. Now, interesting thing is that polymatrices PK and beta L is a multiplicative term. Now you see, just look at it. Look at this term, BL, BK, JL, PK. Similar to the classical neural network weighting to input. And summation part. Same thing done, but in different way or other way around. So now, if you just now the interesting thing is that you have to adjust the parameter. That is the secondary question altogether. But this is quite similar. This is quite similar to the expression to the classical neural network, where a multiplication of a vector and a matrix like this. Now, this you can just simply, if you just look at this expression, UL theta Lj is a combination or a collection of this e to the power minus theta Lj, b theta Lj, and pk. Just using these terms together and just expressing in terms of this cosine and sine, two different components together. Now, interesting thing, these are actually the part of this u theta. It is the variational quantum computer part. That is the evaluating part, training part. Now, obviously, what comes next is the sampling part of the measurement. Now, from the measurement itself, it is quite unusual to get a guess of the parameter value. Now, measurement can be expressed in terms of the parameter theta by using the Hamiltonian, because for any particular quantum system, the Hamiltonian itself the energy of the system. So, the energy of the system on the expectation term is given by theta is equal to inner product of 50, get 50 and get 50, and giving this u diagram and u and Hamiltonian. Okay. So from here only, you can get an idea about the influence of theta on the expectation value. So the adjustment of theta of the quantum model will ultimately induce some changes in the expectation value. Okay. So now these are all mathematical manipulation. This can be expressed. This h can be expressed in this particular form, alpha into h, alpha dot h, where individual hk is given by h theta. It is a function of theta. Okay, so this is the f theta h. So f theta part can be further expressed as a function of alpha dot h theta, where they are commuting terms or non-commuting terms. That depends. Now, for the mathematics itself, so here you have just expressed this f theta. Express this f theta in terms of the vectors s theta, with the alpha parameter being the multiplicative term or the manipulating term, but s theta can be represented by h theta like this form, in this Hamiltonian form, and you got an estimate. That means the estimate of the f theta, that what tantamount to, because you have the estimation of the cost function of the quantum model. Now, quite obviously, now once you come back to the classical domain, the remainder is the gradient descent. So you have to have because the f is actually, expectation value is actually coming out to be random because of the random choices of the 5 parameters in the quantum model, in the parameterized quantum circuit, random choices. So quite obviously, it is. So you have to take that, because theta is the culprit. Theta being the parameter of the parameterized quantum circuit, u theta. So theta being the culprit, you have to take the derivative of f with respect to theta. Now f can only be derived rather than use this form until and unless you cannot make a sample. After sampling, you get the classical value. You can just have the derivative with respect to partial derivative with respect to theta. So now, interesting thing is that you can directly have the similar to the classical neural network. You can have direct correspondence between f and theta. What you can do, you can just use the expression for a chain rule like this: del f del theta k and del theta k del theta. Now you see, del f del theta k is actually beta from the previous notation. So ultimately, the expression comes out to be a theta. A theta is actually the perturbation. A theta is given by similar expression. F theta in terms of f theta, k50, u delta, the function of theta, and u function of theta, Hamiltonian h, where individually you are going to ultimately getting the gradient descent of f theta or f theta, what may be the case, like this: del del j, del del theta, f theta, a theta is a small perturbation, because of the Hamiltonian. A small perturbation always gets back to the original energy value. So it can be expressed as a perturbation of two perturbations. Actually, it's by last pi by 4 and minus pi by 4. The difference of two perturbations together. So thank you, sir. It boils down to this very interesting scenario. You have a deep neural network, hybrid quantum classical, or classical quantum classical, classical quantam classical. Deep neural network classical, it actually calculates the theta of the parameters quantum circuit. The theta has been put in the QNN, QNN to the Hamiltonian expectation function sampling. It can be adjust the loss function L and produces new delta loss function with respect to delta Hamiltonian. It is the expectation value, and then you get a GJ. This GJ has been fed to a quantum neural network. The GJ is a generator function, and then ultimately you get back the GJ in terms of delta theta k, because ultimately theta is going to be adjusted with respect to delta L, delta theta k. And then you finally again put that back into a deep neural network for getting the updated value of theta j, which has to be fed again. So this process actually can come. So you can just, if you just look in terms of a architecture like this is a DNN. You have the ultimate the TNN is giving you theta 1, theta 2, theta 3 for this parameterized quantum circuits. And this is being sampled and the Hamiltonian is being produced like this. And they are being fed to the DNN again or classical neural network to get the loss function. Loss function is being optimized with respect to get the GJ. GJ is being fed to the QNN, and GJ is ultimately derivative of GJ will give you the derivative of loss function with respect to theta, because theta is the actual parameter to be adjusted, which is again to be DNN. So you can just visualize them like this, because you have to have some classical model to support your quantum model. So there are some snapshots. Just see the difference. Quantum neural network, pure quantum neural versus hybrid CNN. Here is a comparison to quantum convolutional neural network. Hybrid CNN is multiple quantum features. You see a pure quantum neural network that has this particular curve like this, the blue one. Very, very slow convergence. This blue one. Okay. And the hybrid CNN is giving you the red line like this. But hybrid CNN with multiple quantum filters in between will give you the best performance in terms of the convergence. So the moral of the story is that you must have a classical algorithm in place to support your quantum machine to get the best performance out. Now, quite obviously, because you see when you just implement this on a NISQ device, you have the errors over there, okay? So the performance is degraded. So the classical algorithm takes care of this loss of performance, the degradation of performance, and tries to boost the neural network, quantum neural network accordingly. That is why you are getting a very good performance when you are applying a hybrid CNN using multiple quantum filters. Now this is all about the performance comparison. Now you have some examples like this, quantum CNN. How can you develop a quantum CNN for images? So this is an architecture. So you have some quantum filters like this over here, some part. But if this convolution pooling and all these things. So you can have this something like this. So you see inputs, the matrix can be just encoded like this. If you just remember the encoding, similar. If you just remember this encoding, similar to the quantum neural network. Encoding different thetas coming to the quantum model. This is the data encoding part, the fixed state, and this is the different PQC or PQC. And then you get the measurement, and then finally you have this output feature map. So you have so in any way you have to have a classical model and a quantum model together. Now, interesting thing is that if you just go back, I don't know whether this is. Oh goodness. Oh, sorry. This one. You see, this was a classical neural network or a cost function. So you can use different types of neural networks as such. So in this particular treatment, we have resorted to the recurrent neural networks. Just hold on. Oh, sorry. You can optimize the variational parameters using RNN. Very interesting. You can have a RNN types of, just replace the classical model in RNN, and all the quantum neural networks are still there. So RNN takes the theta minus 2 from the previously predicted theta value. Previously predicted sampling value, Y, and previously predicted Hamiltonian value of the previous general iteration. And then you just have to predict the t minus 1 for the next one, theta t minus 1 for the next one, yt minus 1. Yt minus actually the Hamiltonian loss function. Okay, I told you earlier using the DNN, CNN, DNN, QNN, and DNN. And then this can be used again to predict the YT, theta T, and ST. And this, if you just go it further, you can have the further levels of recurrence. So recurrent neural networks can be one of the options to optimize the variation of quantum circuit. So this is all about what I told you. Just simply, actually, what you are doing, you have an RNN with a theta phi parameter, classical model. It takes into account the HT, Hamiltonian, of the previous iteration. Theta, previously predicted, and Y is the previously predicted sampling value, expectation value, or the Hamiltonian expectation value. And then it actually predicts HT plus 1 and theta T plus 1. So see the difference between quantum optimization versus standard gradient descent. Standard gradient descent has this particular curve. The cost function, the decay of cost function is slower compared to the LSTM, that is using recurrent neural networks. So recurrent neural networks are a good candidate for optimization of the variational parameters. And finally, one example, how to encode or just design a classic quantum autoencoder. A classical autoencoder, inputs and outputs are there. You have to have a difference, try to minimize the difference. You have a distribution and just recognition and reconstruction, and just try to have some reduction of the, or rather you try to extract the features, and from the features you get the original output. So some example will be like this, quantum variational encoder. So here you have the very interesting encoder part and decoder part. You start with, say for example, 1, 2, 3, 4, 5, 6 qubits. You just measure out 3 qubits. Ultimately you end up with 3 qubits. And then you just supplement the 3 qubits, that is the feature, with these ancillary qubits, get 0, get 0, and get back the 6 qubits again, the decoding part. You start with the 6 qubits, you end up with 6 outputs. In between, there is a feature extraction and reconstruction. Okay, so this is a schematic diagram. I'm not going into detail. You can have this one like this. These are qubits, out of which some of them are being clashed out. This part is the complex state, there is features. And then by using the swap gate and using the ancillary qubit reference state, because ultimately you have to have some comparison with the reference state. Comparison with the reference state. So with the reference state, by using the swap gate, you can have a comparison by using the ancillary qubits. You can just use the cost function, computing the cost function and optimization in the classical domain, and new set of parameters for the U theta or U parameter of the variational quantum circuits. So this will be one of the realizations of this entire thing in practice. So finally, touching upon different QNN models, this one we have discussed, quantum MPA neural network. You can have quantum competitive neural network, dot neural network, cellular neural network, qubit neural network, associative neural network. Nowadays we have the quantum DNN, single qubit quantum ResNet and all these things, whatever works, just published, single qubit ResNet. And then, so what is the deliverable of this particular topic? First of all, remarkable abilities of QNN, to generalize, tolerant to noisy data, and quite obviously taking the help of classical neural network, you are just obeying the actions of Baron-Pareto, which is a quite common practice in the optimization procedure. You come back to stuck to the local optimum. So use the classical neural network to get rid of the local optimum and come back to the global optimum values of the parameters accordingly. And what are the advantages? Exponential memory capacity. Now, very interesting. This is what we have done is single layer neural network solution of linearly inseparable problems. Now, you see, if you just recollect a classical neural network, OR gate can be simply implemented or simulated by a basic perceptron. If you go to the XOR gate, you have the nonlinearity. You have to have a hidden layer. But interestingly, if you just use a single layer neural network in a qubit neural network can solve linearly inseparable problems. Okay, and fastest processing speed. These are quite impelling and compelling in nature. So it opens up a discussion or some of the different references you can have. And finally, thank you for bearing me all this time.
So with this, I would like to thank the speaker again.
Thank you very much.
And, I would like to thank the audience as well for such a number of participants. And yeah, there is some satisfaction survey in the chat. And our next quantum computing seminar will be in November, but the invitation will be sent via standard channels. So have a nice rest of the day, and see you probably on the next seminar.